Hi everybody, this is Mr. Short. Today we're going to be learning about electron configurations, or said another way, how electrons are arranged inside an atom. To put this into perspective, remember we just got done with section 1.1, where we learned about an introduction to atomic structure. We learned about things like where the protons and neutrons are at, that the electrons are outside of the nucleus, and we learned about some of the experiments by Thomson and Rutherford that led to our understanding of modern atomic structure. Now today we've got 4 objectives. And these objectives are to write complete electron configurations. And again, electron configurations show the arrangement of electrons inside atoms. We'll also take a look at the structure and organization of the periodic table. In particular, we're going to take a look at 4 sections or blocks on the periodic table called the S, P, D, and F blocks. We'll learn about a shortcut called an abbreviated noble gas electron configuration. And we'll also address the question, what happens when atoms turn into ions? Now first of all, S, P, D, and F are called blocks on the periodic table. These are different sections on the periodic table, and they're important for understanding electron configuration. So what do they mean? S, P, D, and F refer to sublevels within what are called a Principal quantum energy level. These sublevels are located here in the S block, in the P block over here, in the D block over here, in the F block right over here. So as we go through in this section, I think you're going to see a lot of similarities between structure and organization of the periodic table and the arrangement of electrons inside atoms. Okay, the other thing that we can get from this particular picture right here is it shows what order we write the electrons in the electron configuration. So for example, we would start out at the top with 1s here and here, and then we would go down to 2s, and then we would go across to 2p, and then we would go down to 3s, across to 3p, down to 4s, to 3d. I know that seems like it's out of order, but that's the way that it goes, and then up to 4p. And that's all that we're going to do in this class, is up to 4p. So we should start with the question, how many electrons can each sublevel hold? The S sublevel holds 2 electrons, and I want to go back to the previous slide and point out that the S block has 2 columns inside the S block. Likewise, the P sublevel can hold 6 electrons, and the P block has 6 vertical columns. 1, 2, 3, 4, 5, 6. So remember, the S block is here. The S sublevel holds 2 electrons. P block is right here. P sublevel holds 6 electrons. The D block is here. It holds 10 electrons. F block is here. F sublevel can hold 14 electrons. So 2, 6, 10, and 14. Now you'll write so many of these that you end up memorizing these numbers, but just notice that it's a sequence. 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. Alright, let's take a look at an example of an electron configuration, and I've written the order of electron configuration right up here. If we think about the element arsenic, arsenic in its neutral state has 33 protons, and in its neutral state, it would also have 33 electrons. So we want to figure out how to represent the electron configuration for neutral arsenic, which has 33 electrons. This would be the neutral electron configuration for arsenic, which has 33 electrons. Notice that we start at the beginning of the electron configuration, 1s, and we fill that sublevel up completely. Now remember, the S sublevel can hold 2 electrons. Then we write the next sublevel, which is 2s, fill it up completely. Next sublevel, which is 2p, we fill it up completely. The P sublevel holds 6 electrons. 3s, 3p, 4s, and then remember, after 4s does come 3d, and a D sublevel can hold 10 electrons. So 3d, 10. And if we stop right here and we add up these exponents up to and including 3d10, the exponents we're going to find, they represent the electrons. So 2 plus 2 plus 6, that adds up to 10. Then 2 plus 6 plus 2, that's another 10. So right here we've got 10, here we've got 10, that's 20. Here's 10, so that adds up to 30. And then we need to stop at 4p3 because the sum of these exponents now adds up to 33, and we want to represent 33 electrons for neutral arsenic. Here's another example. Let's see if we can do this. We've written a complete electron configuration below, 1s2, 2s2, 2p6. So the question is, how many electrons does this neutral element have, and what is the symbol for this neutral element? Go ahead and hit pause and figure that out. So remember, the sum of the exponents adds up to the number of electrons, and since this is neutral, the number of electrons would also equal the number of protons. Since the exponents add up to 10, this must have 10 electrons in its neutral state. And the element that has 10 electrons in its neutral state is neon. Okay, neon is the element that has 10 protons and 10 electrons. All right, let's take a look at something called a noble gas electron configuration, or an abbreviated noble gas electron configuration. First of all, we need to know where the noble gases are located on the periodic table. The noble gases are on the far right-hand side of the periodic table. They're in so-called column 8 or main group 8. It starts with helium and ends with radon right over here. So it goes helium, neon, argon, krypton, xenon, and radon. Those are the noble gases. We're going to use those as a shortcut, and we're going to see why. Okay, so noble gas electron configurations. The noble gases are listed right there on the far right-hand side of the periodic table. And what we might notice is that each one is at the very end of that particular row. It's on the far right-hand side of each horizontal row on the periodic table. Noble gas configurations take advantage of this by condensing what you have to write something that looks like this. So let's take a look. All right, helium is element number 2. In its neutral state, it would have 2 protons and 2 electrons, and its electron configuration would be 1s2. But we can abbreviate this, and we can just put bracket helium, and that's the way that we say this, bracket helium. Bracket helium means 1s2. Here's another example. So let's say that we're dealing with carbon. Carbon is not a noble gas, but carbon in its neutral state has 6 protons and therefore 6 electrons. Its complete electron configuration would be 1s2, 2s2, 2p2. That adds up to 6. And take a look. Because carbon has this 1s2 in it, and we know that 1s2 is equal to bracket helium, we can do a little substitution here. And we can say that the noble gas configuration for carbon is bracket helium, 2s2, 2p2. See how all we did there is a little bit of substitution. We substituted bracket helium for 1s2 to get bracket helium, 2s2, 2p2. By the way, that should be a superscript right there. All right, let's take a look at another example. All right, here's an example for arsenic. We took a look at arsenic earlier, and we saw that arsenic in its neutral state has 33 electrons. And this would be the complete electron configuration for arsenic. Remember, the sum of the exponents has to add up to the total number of electrons in this particular substance, and those exponents add up to 33. Okay, notice this part in yellow though, it's the same as argon's configuration. And argon is one of those group 8 noble gases. Argon's configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So the noble configuration will start with the gas that's in the row before it. So for this up here, we can do some substitution, and we can say that all of this in yellow equals bracket argon, and then we just need to continue beyond it. 4s2, 3d10, 4p3. So remember, bracket argon equals 18 electrons. Let's confirm that. 2, 2, and 6 is 10, plus another 2 and another 6 adds up to 18. So this means the first 18 electrons, there's 20, 30, 33. And that's how we can use this shortcut with an abbreviated noble gas electron configuration to represent the electron configuration for arsenic. Okay, and it does cut down on a lot of writing, and that is a good thing. All right, let's take a look at a couple more examples. Up top, I've put two complete electron configurations for two of the smaller noble gases, and I've written their very simple noble gas configuration. And then down here, I've written, okay, sodium in its neutral state has 11 electrons, so 2, 2, 6, and 1 adds up to 11. Since neon ends in this configuration 2p6, we can substitute bracket neon to mean the first 10 electrons, and then we just continue on from there. But take a look. When sodium turns into sodium ion, it takes a positive charge. And the way that it takes a positive charge is by losing this 3s1 electron. So now, this would have 10 electrons, and it would be 1s2, 2s2, 2p6, and that is the configuration for neon. So we can just abbreviate sodium ion as bracket neon. If you take a look down here, chlorine in its neutral state would have 17 electrons. 2, 2, 6, and 5 adds up to 17. What we can do is we can use bracket neon to represent the first 10 electrons and then continue on from there. 3s2, 3p5. So remember, this is 10, there's 12, there's 17. That's how many we want. When chlorine turns into chloride ion, it gains an electron. So it no longer has 17 electrons, now it has 18 electrons, and that new electron is this 3p6 electron right here. So take a look. Chloride ion would now have 2, 2, 6, 2, and 6. That adds up to 18 electrons. So I want you to take a minute and I want you to predict the abbreviated noble gas configuration for chloride ion. That's right, chloride ion would have the abbreviated configuration bracket argon, because remember, argon is the noble gas that has 18 electrons. So in general, I want us to summarize what happens when an atom turns into an ion. When an atom turns into an ion, the ion will look like a close, is it alkali metal, alkaline earth metal, halogen, or noble gas? Pause and make a prediction about what that is. That's right, the answer is noble gas. Okay, so when an atom turns into an ion, it will look like a close noble gas. Now what I mean by look like is that it has the same configuration as a close noble gas here or here, but it does not have the same number of protons as a close noble gas. Alright, so let's review real quick. On the left-hand side, I've got the objectives, and on the right-hand side, I've got some examples. So we took a look at how to write things like electron configurations. For magnesium, for example, since magnesium in its neutral state has 12 electrons, its complete electron configuration would be 1s2, 2s2, 2p6, 3s2, because of the sum of the exponents adds up to 12. Its abbreviated noble gas electron configuration would look like this. We can use bracket neon to mean the first 10 electrons ending in 2p6, and so we can say that it's bracket neon 3s2. We also took a look at the structure and organization of the periodic table. In particular, we said that this is called the S block right here. It's got 2 columns. This is the P block right here. It's got 6 columns. D block has 10 columns. And F block has 14 columns. And that relates to the maximum number of electrons that can be held in each sublevel. We also took a look at what happens when an atom turns into an ion, and we said it will look like a close noble gas. Here we've got an example down here. When neutral magnesium loses these 2 electrons to turn into magnesium ion, it now has the same electron configuration as neon, so we can say bracket neon is the new electron configuration. All right, thanks a lot, guys. Have a great day.